Welcome back to the deep dive. I'm really glad you're joining us. Today, our mission is, we're taking a deep dive into the fascinating world of Group 2 elements. You probably know them as the alkaline earth metals. We're going to be sifting through a really key chapter from Shriver and Atkins Inorganic Chemistry, our goal. To bring these sometimes complex concepts to life, make them clear, engaging, especially if you're a college student, and importantly, without needing any visuals.
That's exactly right. Think of this as maybe a shortcut, a way to really grasp these elements. Over the next few minutes, we'll look at their fundamental properties, the basics. We'll uncover where they're actually found in nature and then get into the surprisingly diverse chemistry of their compounds, from the really simple ones to the more complex structures. And we'll definitely draw some key comparisons with their neighbors, Group 1. And like you said, we have to shine a spotlight on beryllium. It's kind of the rebel of Group 2.
Oh, absolutely. And trust me, these elements, they're literally everywhere. They help build our cities, they give fireworks those amazing colors, and believe it or not, they're even parts of, well, us. Our bodies, it's going to be a journey, right from their atomic structure through to their incredible real-world impact. So, yeah, let's unpack this. Hashtag the essentials. Okay, so to kick things off then, what's the first crucial thing we need to understand about Group 2? What are those absolute fundamentals that really shape their chemical personality?
Right. Well, if you want to understand any element's behavior, really, but especially here in Group 2, you've got to start with two main things. Their ionization energies, how easy it is to remove electrons, and their ionic radii, basically how big the ions are. These two factors, they pretty much dictate everything else. Generally speaking, these are silvery white metals. Most in their compounds, they tend to be predominantly ionic. That just means they're formed by, transferring electrons. But here's where it gets interesting, especially compared to Group 1. Group 2 elements are denser, they're harder, and generally less reactive. Though don't get me wrong, they're still quite reactive metals overall.
Okay, denser, harder, less reactive than Group 1. Got it. But where do we actually find them? In nature, I mean. Are they common? Rare?
Oh, many are incredibly common. Take magnesium, for instance. It's the 8th most abundant element in the Earth's crust. And get this, the 3rd most abundant dissolved ion in seawater, that's actually where we get a lot of it commercially, calcium. Even more common, you see it everywhere as limestone, marble, chalk. And it's a huge component of biominerals like shells and coral. Beryllium is a bit different, found in specific minerals like beryl. And then there's radium. All its isotopes are radioactive, so you find it tucked away in uranium-bearing minerals.
Interesting mix. So as we go down the group, from beryllium at the top to radium at the bottom, what happens? What are the patterns in their reactivity?
Ah, yes, there's a very clear trend. As you move down the group, the atoms get bigger, the radius increases. This means those outermost electrons, the valence electrons, are further from the nucleus, less tightly held, so it becomes easier to remove them. Their ionization energy decreases, and the result, the elements become more reactive. More electropositive is the term we use. They're just, more eager to lose those 2 electrons and form that stable M2 plus ion. You can see this perfectly in how they react with water. Calcium, strontium, barium, radium, they all react quite readily with cold water, fizz away. But magnesium, being higher up and a bit less reactive, it needs hot water to really get going. The general reaction is always the same, though. Metal plus water gives you the metal hydroxide and hydrogen gas.
Okay, that makes sense. More reactive down the group. Now, here's something I remember from chemistry class, something visually spectacular. Flame tests. What's actually happening there? Why the bright colors?
Flame test. It's a classic. And yeah, visually pretty cool. It's basically energy in action. When you heat salts of the heavier Group 2 elements, calcium, strontium, barium, radium, in a hot flame, their electrons absorb energy and get excited. They jump up to higher energy levels. But they don't stay there long. As they fall back down to their normal state, they release that extra energy as light. Crucially, they release it at very specific wavelengths, specific energies. And that's what gives us those distinct, really beautiful colors. Calcium gives off that characteristic orange red, strontium, a really brilliant crimson red, barium is a sort of yellowish green, and radium, a deep red. These colors aren't just for, identifying them in the lab. They're famously what make our fireworks so spectacular.
Right, fireworks. I knew there was a connection. Okay, let's move on to their simple compounds. You mentioned they all pretty much exist in the MII oxidation state. What does that tell us about their basic chemical building blocks.
Yeah, that MII state is fundamental. It all comes back to their electron configuration, their outer shell. It's NSS, right? They have those two valence electrons, and they're relatively easy to lose to get a stable noble gas configuration underneath. So forming that M2 plus ion is really favorable for them. And for the most part, the compounds they form with nonmetals are ionic. Think positive M2 plus ions and negative anions held together by electrostatic attraction. Let's maybe look at their hydrides for a second. Most of them, so magnesium down to radium, they form ionic hydrides. Saline hydrides, we call them. They contain the hydride ion, H. Straightforward enough. But then you have beryllium hydride, BH2. And it's fascinatingly different. It's not ionic, it's covalent, and it doesn't form a simple linear molecule like you might expect. Instead, it forms this complex polymer, a network structure with beryllium atoms linked by bridging hydrogen atoms. It's already hinting at beryllium's unique personality. And then there are halides, like MX2, where X is a halogen like fluorine or chlorine. Similar story unfolds. For the larger cations like calcium, strontium, barium, they tend to form typical ionic crystal lattices. Calcium fluoride, for example, has the well-known fluorite structure. But again, beryllium halides, they're different. They form these covalently bonded networks. Often you see beryllium surrounded by four halogens in a tetrahedral arrangement, and these tetrahedra link up. Much more covalent character. It's a theme you see over and over with beryllium: small size, high charge density, leads to covalency.
Okay, so beryllium keeps breaking the mold. What about their oxides and hydroxides? Does that pattern hold true there as well?
Absolutely. Beryllium oxide, BeO. It's a white solid, doesn't dissolve in water, and it has its own unique crystal structure, the Wurtzite structure. Here, each beryllium is bonded to four oxygens and each oxygen to four berylliums. It's a four coordination. Now compare that to the other group 2 oxides, MgO down to RaO. They adopt the much more common rock salt structure, like sodium chloride, with 6 coordination, clearly ionic. Their reactivity with water also shows a trend. Magnesium oxide reacts, but slowly. Strontium and barium oxides react much more readily, forming strongly basic hydroxide solutions. And then there's beryllium hydroxide, BOH2. It's really interesting because it's amphoteric. That means it can react as both an acid with strong bases and as a base with acids. The other group 2 hydroxides, they're just basic. Magnesium hydroxide is sparingly soluble and basic, calcium hydroxide more so, and barium hydroxide is quite strongly basic. So yeah, amphoterism is another special feature of beryllium chemistry.
Amphoteric. Okay. It acts as both acid and base. Right. You also mentioned earlier their salts of oxoacids like carbonates and sulfates. Is there a general rule about whether they dissolve in water? Does that help explain why we find them in rocks and minerals?
Yes, there's a very useful pattern here. Salts formed with singly charged anions, think chlorides, nitrates, they are generally soluble in water, easy to dissolve. But salts formed with doubly charged anions like carbonates, CO3-OJOs, sulfates, SO4-rubber, phosphates, PO4-ONO. These are typically sparingly soluble or even considered insoluble. Why? It comes down to the energy holding the crystal together, the lattice enthalpy. When you have +2 carbonations and -2 anions, the electrostatic attraction is really strong. That makes the lattice enthalpy very high, very hard to break apart. Water molecules trying to solvate the ions just can't overcome that strong attraction easily, and that's exactly why we find so many group 2 carbonates and sulfates as natural minerals. Limestone, gypsum, they're stable because they don't easily dissolve. They're also crucial, of course, in biological systems. Think calcium carbonate in shells, calcium phosphate in bones.
Right. The high lattice enthalpy makes them stick together. Okay, so this really brings us back to, well, the star of the show, maybe, beryllium. Why does it really stand out? Why is it the rebel? What makes it play by such different rules compared to magnesium, calcium, and the others?
Beryllium is absolutely the anomaly, the outlier, and it all fundamentally comes down to its incredibly small size. Its ionic radius for B2 plus Gel is only about 27 picometers. That's tiny. This tiny size combined with its +2 charge gives it a very, very high charge density. And this high charge density means it has a strong polarizing power. It pulls the electron clouds of nearby anions very strongly towards itself. The big consequence of this, instead of fully transferring electrons to form ionic bonds, it tends to share electrons, forming bonds with significant covalent character. So its chemistry behaves much more like, say, aluminum or even some metalloids, rather than its metallic group 2 neighbors.
Okay, tiny size, high charge density, pulls electrons strongly, leads to covalent bonds. So for you listening, what are the key takeaways? What are the most important consequences of these unique beryllium properties?
Well, first, like we said, its compounds halides like BCl2, the hydride BH2, they have significant, often dominant covalent character. They form network or polymeric structures, not simple ionic lattices. Second, because of this covalency, it has a much greater tendency to form stable coordination complexes, even with simple ligands. It typically prefers a tetrahedral geometry, 4 bonds. Third, when you dissolve beryllium salts in water, the highly polarizing B2 plus ion interacts so strongly with water molecules that it causes hydrolysis, basically. It makes the water molecules release H plus double, making the solution acidic. Fourth, its oxide and related compounds adopt those 4 coordination structures, different from the 66 structures of the other group 2 oxides. And fifth, it forms many stable organometallic compounds, compounds with beryllium carbon bonds, which are quite interesting chemically. Oh, and one more really important point. This leads to the famous diagonal relationship with aluminum, which is in group 13, period 3. Beryllium and aluminum share many chemical similarities despite being in different groups. Both form covalent hydrides and halides. Their oxides are amphoteric. They form similar complex ions in base. And even their carbides react with water to give methane, which is different from how other group 2 carbides react. It really highlights how beryllium's properties bridge towards other parts of the periodic table. Hashtag the detail.
Okay, that diagonal relationship is a really neat point. Right, now that we've got the essentials down, let's dive into some more specifics of the detail. When it comes to actually finding and extracting these elements, you mentioned magnesium from seawater. What's another really compelling story about getting these metals out of the ground?
Well, the extraction of magnesium from seawater is definitely a highlight of chemical engineering. You basically add calcium hydroxide slaked lime, made from seashells or limestone, to seawater. The hydroxide ions precipitate the much less soluble magnesium hydroxide, MgOH2. You filter that off, then you react that with hydrochloric acid to get magnesium chloride, MgCl2. You dry that very carefully, melt it, and then use electrolysis, passing an electric current through the molten salt to split it into molten magnesium metal and chlorine gas. But the really clever bit, as I mentioned, is handling the molten magnesium. It's very reactive. It even reacts with nitrogen, so you can't just use air or nitrogen as a protective blanket. You have to use an inert atmosphere of something like argon, or even small amounts of reactive gases like sulfur hexafluoride, SF6, or sulfur dioxide, SO2, that form a protective layer.
Wow, reacts with nitrogen. Didn't know that. Okay, and speaking of incredible efforts in extraction, we have to talk about radium, the story of Marie and Pierre Curie isolating it. It's just legendary, isn't it? What made it so incredibly difficult?
Oh, it's an epic story of scientific perseverance. Absolutely legendary. The Curies were working with pitchblende, which is primarily a uranium ore. They noticed it was more radioactive than pure uranium should be, suggesting another element was present. That element was radium. But the challenge, the concentration. Pitchblende contains only about 1 gram of radium for every 10 tons of ore. That's minuscule. They had to process literally tons of this pitchblende residue using laborious chemical separation techniques, dissolving, precipitating, filtering again and again. Fractional crystallization was key. It took them 3 incredibly arduous years working in basic conditions to finally isolate just 1/10 of a gram, 0.1 gram of radium chloride. It's just an amazing testament to meticulous chemical separation and sheer dedication. Truly one of the great scientific detective stories.
Just incredible. 10 tons for a gram.
Wow.
Okay, let's switch gears to applications. These elements and their compounds, they literally help build our world from high-tech stuff to, well, everyday medicines. What's a really striking use for beryllium, given its unique properties?
Beryllium's combination of lightness, strength, high melting point, and relative inertness makes it really valuable in specialized high-tech fields. It's used in precision instruments where stability is key. Also in aerospace aircraft, missiles where lightweight strength is crucial. And because it's almost transparent to X-rays, it's used to make the windows in X-ray tubes, letting the X-rays out without absorbing them much. It also finds use in nuclear reactors as a moderator, slowing down neutrons. Now, we have to mention soluble beryllium compounds and inhaled BeO dust are quite toxic, so handling requires care. But paradoxically, beryllium oxide itself, the ceramic, is actually very useful because of its properties. It has an extremely high melting point and surprisingly very high thermal conductivity for an electrical insulator. This means it's great for dissipating heat in high-power electrical devices and electronics, acting as a heat sink while still being an insulator.
High thermal conductivity, but an insulator.
Yeah.
Interesting combo. Okay, and magnesium, we know it's light. Where does that property really shine, industrially speaking?
Magnesium's lightness is its main selling point for alloys. Mixed with aluminum, it creates alloys that are both strong and very light, perfect for aircraft components, car parts, things like that. There's a historical note, though. Early magnesium alloys were quite flammable, famously causing issues in things like warships, but modern alloys are much safer. You also see magnesium used vividly in pyrotechnics. When magnesium powder burns, it produces an incredibly intense, brilliant white light, perfect for fireworks and emergency flares. And then, of course, there are the medical uses. Many of us have probably used milk of magnesia, that's magnesium hydroxide, MgOH2, as an antacid or laxative. Or maybe Epsom salt magnesium sulfate heptahydrate, MgSO4.7H2O, used in baths for muscle soreness or as a supplement. And MgO, magnesium oxide, is used as a refractory lining in furnaces because of its very high melting point.
Right, milk of magnesia, Epsom salts. Very familiar. Now, calcium. It seems like its compounds are the real workhorses, especially in construction.
Mhm.
Can you maybe unpack the chemistry behind something as, well, fundamental as cement and concrete?
Absolutely. Cement is, it's really a marvel of applied chemistry, foundational to modern construction. The process starts with heating limestone that's mostly calcium carbonate, KCO3, together with aluminosilicates, which you find in clay or shale, in a huge rotary kiln to very high temperatures, like 1450 degrees C. This intense heating causes chemical reactions, driving off CO2 and forming a complex mixture of calcium silicates and aluminates. This grayish nodular material is called clinker. The clinker is then cooled and ground into a very fine powder. A small amount of gypsum calcium sulfate dihydrate, Ki4.2H2O, is added at this stage. Why? It helps control the setting time. And that final powdered mixture, that's Portland cement. To make concrete, you just mix the cement powder with aggregate sand and gravel and, crucially, water. The water triggers a complex series of hydration reactions. The calcium silicates and aluminates react with water to form a dense interlocking network of hydrated crystals and gels. This hydrated cement paste binds the sand and gravel particles together, hardening over time into the strong, durable material we know as concrete. It's really the glue holding our infrastructure together. And beyond cement, other calcium compounds are vital too. Gypsum itself, calcium sulfate dihydrate, is what makes plasterboard or drywall. If you heat gypsum gently, it loses some water to become the hemihydrate, KSO4H2O, better known as plaster of Paris. When you mix plaster of Paris with water, it rehydrates back to gypsum, expanding slightly as it sets, which makes it perfect for making casts or molds. And calcium carbonate limestone isn't just for cement. It's used to neutralize acidic soil in agriculture. It's used in the Solvay process for making sodium carbonate, and even as a simple antacid.
Wow. Okay, cement chemistry is more involved than I thought. So moving down the group, what about, say, barium? You mentioned its use in medicine. Can you elaborate on that?
Right, the barium meal. Barium compounds are excellent at absorbing X-rays. Why? Because the barium ion, Ba2 plus Mache, is large and has a lot of electrons, 54 of them, in fact. These electrons effectively stop X-rays from passing through. So if you want to visualize the digestive tract, which normally X-rays pass straight through, you have the patient drink a suspension of a barium compound. This coats the inside of the esophagus, stomach, and intestines, making them show up clearly on an X-ray image. Now, the critical detail here, and it's really important, is that soluble barium compounds are toxic. Barium ions can interfere with potassium ion channels in the body. So for medical imaging, they use barium sulfate, ASO4, which is extremely insoluble in water and body fluids. Because it's so insoluble, it just passes through the digestive system without being absorbed into the bloodstream, making the procedure safe. Barium carbonate, BaSO3, is also used in glass making, and less pleasantly, as a rat poison, exploiting barium's toxicity when ingested in a soluble form.
Ah, the insolubility is key for safety.
Got it. And just to circle back before we move on, let's not forget the huge biological importance of magnesium and calcium. They're not just rocks and metals, they're vital for life itself.
Absolutely vital. Couldn't agree more. Magnesium, for example, sits right at the active center of the chlorophyll molecule. That's the green pigment in plants that captures sunlight energy for photosynthesis. No magnesium, no photosynthesis as we know it. Magnesium ions are also essential for the function of ATP, the main energy currency molecule in all our cells. And they act as cofactors, activating hundreds of different enzymes involved in countless metabolic processes. Calcium, well, its role is perhaps even more obvious structurally. It's the main mineral component of our bones and teeth, usually as calcium phosphate, hydroxyapatite. It forms the hard structure of shells and coral, too. But beyond structure, calcium ions, Ci2+, are incredibly important signaling molecules within our cells. Tiny changes in calcium ion concentration trigger all sorts of processes like muscle contraction, nerve impulse transmission, hormone release. It's involved in so much cellular communication. It's amazing how these simple ions play such complex roles. Okay, let's quickly revisit hydrides. You mentioned BH2 being covalent and polymeric. What about the others like MgH2? Any interesting applications?
Yes, MgH2 magnesium hydride is ionic, like the heavier ones, and reacts with water to release hydrogen. But what's particularly interesting about MgH2 is its potential for hydrogen storage. Hydrogen is a clean fuel, but storing it safely and efficiently is a major challenge. Magnesium metal can react directly with hydrogen gas under pressure to form solid MgH2, effectively storing the hydrogen in a compact solid form. MgS plus H2G reversible reaction arrow MgH2. Then, when you need the hydrogen, you can heat the MgH2 and it decomposes back into magnesium metal and hydrogen gas. The reaction is reversible. The main hurdle right now is that you need quite high temperatures, around 300 degrees C, to release the hydrogen at a useful rate. So, a lot of research is focused on finding catalysts or modifying the MgH2 to lower that decomposition temperature, making it more practical for things like hydrogen-powered vehicles.
Hydrogen storage, that's definitely cutting edge. Now, the halides. We know BiCl2 is covalent, CampHO2 is ionic. What about calcium chloride, CaCl2? It seems pretty common. Why is it so useful, especially in winter?
Calcium chloride, CaCl2. Yes, it's a very useful bulk chemical. One of its key properties is that it's highly hygroscopic. That just means it readily absorbs moisture from the air. This makes it an excellent drying agent, used in labs and industry to dry gases or organic liquids. You often find it as little white pellets. But its biggest use, as you hinted, is probably as a road de-icer in winter. It's often preferred over common rock salt, sodium chloride, and NaCl, especially in very cold climates. Why? Two main reasons. First, when CaCl2 dissolves in water, the process releases quite a bit of heat. It's an exothermic dissolution. This heat helps to melt the ice faster. Second, a solution of calcium chloride in water has a much lower freezing point than a solution of sodium chloride. It can lower the freezing point of water down to about minus 55 degrees Celsius, minus 55 degrees C. Sodium chloride only gets you down to about negative 21 degrees C. So CaCl2 keeps roads ice-free at much lower temperatures. That heat release also means it's used in those instant chemical hot packs.
Minus 55, that's impressive. Okay, let's jump to carbides. You mentioned BDC gives methane, but the others give ethane, acetylene, and you hinted at a historical impact.
Yes, it's a really neat piece of chemical history. Beryllium carbide, B2C, reacts with water to produce methane, CH4. But the carbides of the other group 2 elements, which have the formula MC2, like Pc2, calcium carbide, react with water to produce ethane, C2H2, commonly known as acetylene. Now, calcium carbide, Kc2, became readily available in the late 19th century thanks to the development of electric arc furnaces, and its reaction with water to produce acetylene gas was quickly exploited. Acetylene burns with a very bright, luminous flame. So calcium carbide became the fuel source for acetylene lamps. These were used widely before electric lighting became common for vehicle headlights, cars, bicycles, and perhaps most importantly for miners' cap lamps. It provided a relatively safe, portable, bright light source, which was a huge improvement over candles or oil lamps, especially underground. It genuinely enabled safe nighttime travel and transformed mining safety.
Wow, miners' lamps ran on acetylene from calcium carbide.
Fascinating.
Okay, solubility again. We talked about lattice versus hydration enthalpy. Why are group 2 compounds generally less soluble than group 1? And can you explain the BF2 anomaly again?
Right, the solubility puzzle. It's all about that balance. Lattice enthalpy is the energy needed to break the ionic crystal apart. Hydration enthalpy is the energy released when the separated ions get surrounded by water molecules. For a salt to dissolve, the hydration enthalpy released must be large enough to overcome the lattice enthalpy required. Now, group 2 ions have a +2 charge, compared to +1 for group 1 ions. This means the electrostatic attraction between the M2 plus cations and the anions in the crystal lattice is much stronger. So group 2 compounds generally have significantly higher lattice enthalpies than their group 1 counterparts with the same anion. This makes them harder to break apart and therefore generally less soluble.
Higher lattice enthalpy due to the +2 charge. Makes sense. So why is BF2 soluble when other group 2 fluorides like MgF2 or KF2 are pretty insoluble?
Beryllium fluoride, BF2. It's the classic exception that proves the rule, or rather, shows the importance of both factors. Yes, MgF2, KF2, SRF2, BF2 are all quite insoluble, consistent with high lattice enthalpies. But BF2 is soluble. Why? While its lattice enthalpy is high, the hydration enthalpy of the tiny B2 plus ion is exceptionally large. Remember how small B2 plus is? Water molecules, being polar, are very strongly attracted to that small, highly concentrated positive charge. The energy released when water molecules solvate the B2 plus ion is so massive that it actually overcomes the large lattice enthalpy of BF2. For the larger group 2 ions, Mg2 plus Ca2 plus Nali, etc., their hydration enthalpies are still significant, but not large enough to overcome the lattice enthalpy of their fluorides. It's a beautiful example of how the interplay between lattice and hydration enthalpies, both influenced by ion size and charge, dictate solubility. And that very strong interaction between B2 plus and water also explains why beryllium salts hydrolyze in water, making the solutions acidic. The B2 plus ion polarizes the water molecules so strongly that it helps them lose a proton, H plus.
Okay, the huge hydration energy of tiny B2 plus wins out for BF2. Got it. Last big topic, organometallic compounds. Sounds complex. What's the headline news here, especially for, say, organic chemistry students?
Organometallics compounds with metal carbon bonds. For Group 2, the absolute headline news, the Nobel Prize-winning discovery, is Grignard reagents. These are organomagnesium halides with the general formula RMGX, where R is an alkyl or aryl group, like methyl ethylphenol, and X is a halogen, usually chlorine, bromine, or iodine. They're named after Victor Grignard, who discovered them around 1900. How do you make them? You react magnesium metal turnings with an organohalite, like bromothane or chlorobenzene, in a dry ether solvent, like diethyl ether or THF. The magnesium inserts itself into the carbon-halogen bond. Why are they so incredibly important? Because the carbon atom bonded to the magnesium behaves as if it has a negative charge. It's a carbanion source, a powerful nucleophile. This allows organic chemists to easily form new carbon bonds by reacting Grignard reagents with things like aldehydes, ketones, esters, epoxides. Building complex organic molecules relies heavily on making CC bonds, and Grignard reagents provide one of the most versatile and widely used ways to do that. They absolutely revolutionize synthetic organic chemistry. They exist in solution as a complex mixture of species, known as the Schlenk equilibrium, but their reactivity is generally predictable as R. Beryllium also forms organometallics, like dimethyl beryllium, which has interesting structures, but they aren't nearly as widely used as Grignards. And just as a final note on magnesium surprises, very recently, chemists have managed to synthesize stable compounds containing a direct magnesium bond, essentially MgI compounds. It just shows that even for elements we think we understand well, like magnesium, there can still be new and unexpected chemistry waiting to be discovered. Hashtag outro.
Absolutely fascinating. Grignard reagents, Mg bonds. Amazing stuff. And there you have it. You've just taken a pretty deep dive into the remarkable world of the Group 2 elements. We've journeyed from, their basic atomic properties and reactivity trends, all the way through their often intricate compounds, their extraction, their widespread applications. And we definitely kept a close eye on that unique rebel beryllium.
Exactly. We've seen the clear trends down the group, increasing reactivity, changing structures. We've unpacked that crucial balance between lattice and hydration enthalpies that govern solubility. And hopefully you've got a real sense of the profound impact these elements have, from the rocks beneath our feet to the buildings around us, and even within our own biological systems. Understanding these foundational concepts from Group 2 chemistry is, it's really key to understanding so much more in chemistry.
It really is. So here's a thought to leave you with. Next time you hear about sustainable building materials or advanced medical imaging techniques, maybe catalysts for hydrogen storage, or even discussions about the chemical origins of life, what new connections might you draw back to the versatile, sometimes surprising, always important chemistry of these Group 2 alkaline earth metals? Think about it. Thank you so much for joining us on this deep dive.
Yes, thank you for listening.
And a very warm thank you from the whole Last Minute Lecture team.